So the next two lessons, I don't know what we'll do today. If we get through both, we do. If we don't, we just do part of it tomorrow. That's fine too. They both kind of blend together. They're called trigonometric identities. And I think what I'd like to do actually is show you where we're going to be working off of. On your, what did I just click on there? On your guys' formula sheets, there's a whole bunch of rules. We really haven't talked about, well, any of these. I guess the first one. Covered that one. So my goal over the next 2 days is to talk about how all the rest of these work. And kind of like physics in a way, where this is like your formula sheet, and all of these are formulas. And if you know how to use a formula, it's really all the same. So my goal is just to kind of walk you through what all these formulas mean and what they do and where they might be useful. Does that make sense? So I think my goal was for the first lesson was to cover, I think probably all of these ones here. But anyways, we'll try to get through as many of them as we can today as I can. So let me go back to my first slide. If I talk about an equation, for the last, I don't know, 2 years I've been teaching you guys, we've been focusing a lot on equations. An equation is a function. You guys probably know that term, right? Where you have y equals something. And in that something, you have probably x, right? It could be y equals x squared. It could be y equals 1 over x. It can be y equals sine x or y equals log x. Right? Those are equations, and when you solve an equation, you get an answer. Sometimes you get more than one answer. For example, when you solve a quadratic, you can get 2 answers. Does that make sense? When you solve a cubic, you could get 3 answers. When you solve something for sine and cosine, you could get, a million, infinite answers, and they're all separated by 2 pi. Well, what makes a trigonometric identity weird and different is that it's still an equation, but literally every single value of x is true. Let's say that one more time. You're not solving these, because that's not the point. The point behind them is that every single x you plug in is true. Like every number in the world is an answer to this equation. Does that make sense? So like I'm not even talking whole numbers. Like the number 1 would work on both sides of the equation. The number 1.01 would work on both sides of the equation. The number 1,000,005 would work on both sides of the equation. And that's what makes these things odd. Is they're more like the term we use in math when something is always equal is called identities. Like, for example, this is an identity. Granted, this isn't algebra yet, but like 1 plus 1 is 2. That's an identity. That is always true. But like maybe here's a different example. If I gave you 4 over 2x, that's equal to 2x. If I plug in any number, 1, 2, 3, 0, 5, for x, it's the same on both sides. Does that make sense? Let me start off by showing you one that we've already kind of done. Cosecant x is the same thing as 1 over sine x. Well, those literally mean that they're the exact same thing as each other. Now, we can't actually type in a cosecant. So whenever we use our calculator, we actually type in the identity of sine x, or we sometimes do sine x, and then we do like that -1 thing right there. Every single value of x, that's true for. Sometimes there's a few exceptions. Like, for example, you can't let the bottom of a fraction be 0. So whatever sine of x would be 0, that we can't do. But every other number, it's true for. I've actually already shown you another example of an identity before. It involves sine and cosine. Remember how I kind of have a little joke where a sine graph and a cosine graph are related? And the cosine graph is a sine graph that's failed a grade? Remember that analogy? Well, then what you could say is that a sine graph is equal to a cosine graph minus 90, meaning you got to slide the cosine graph over 90 degrees, and then they're basically the same as each other. Or the opposite of that would be the cosine graph is like if you take the sine graph and shift it that way, 90 degrees. And it doesn't actually matter what value of x you pick, this is always true. Let's just prove it with a few examples just to make sure. So, give me a number for x. Sure. I don't even care whether it's in radians or degrees, it shouldn't matter. So I'm going to find the sine of 2. And then I'm going to find the cosine of 2 minus 90. That should be the same. I don't care what number you pick. Literally, this is true for every number. So we'll just do one more here. I'll just do the other one. Cosine of 12.3968. Just going to be a smart ass. And then we'll do the sine of 12.3968, but then we'll add 90. Exactly. That makes sense. So identities are weird because the goal of them is not to solve. Because if I ask you to solve them, every single number in the universe that you can imagine, decimal number, fraction, negative, whatever, right? Every number should work. So we use them though as like, you know how in physics sometimes you take one formula and you kind of put another formula inside that formula and you kind of manipulate them together? That's what we use these for sometimes, is in like algebraic manipulation exercises. Try some more examples. There are a whole bunch of known identities, and so most of these are on your data sheet. I found this on the internet somewhere. These are the ones, though, that you are expected to be able to work with. They're the ones that are on your purple sheet. Okay. One of the things you may get asked to do then is to prove that an identity is true. I'm going to ask you to do this because I don't know, some kind of an old school teacher. I'd like to show you what I was taught, because I think there's some value in that. You're not going to be asked to prove an identity, though, on the diploma, because that would be like a written response kind of question, and they don't do that anymore. But I still think there's some value in me showing you what I was taught when it comes to this. So here's some hints for proving identities. The first one is probably the one that confuses most people. You actually are going to want to start with the more complicated side. That seems odd, because you're like, why do I want to start with something that looks more difficult? But our goal is going to be to algebraically manipulate the thing that's more challenging. You know what? Maybe I'll just talk about these, though, as I do an example. So here, let's try this first one here. Okay. So you're not going to get asked to do this on a diploma. It's just not. That's not how they phrase questions. But I think there's a lot of value in showing you this. So the way I was taught, and the way that even old diplomas that used to have written response, they used to put like a little bit of a T-chart, and you'd write, this is the left-hand side, and this is the right-hand side. And your left-hand side is the tan of theta minus the sine of theta, divided by tan theta times sine theta. And your right-hand side is the other side of the equation, 1 minus cosine theta over sine theta. What our goal is now is to try to algebraically manipulate either side and try to make it so that both sides are the exact same as each other at some point. I may just need to do an example just to kind of show you what I mean. So, one of the first identities then that I need to show you that I kind of skipped over a few slides ago are these ones here. Because sine is equal to x over r and cosine is y over r and tan is x over y, these ones you might already know. Like the cosecant is when we reciprocal a sine. Cotan is where you reciprocal a tan. Secant is where you reciprocal a cosine. Well, there's another one we've discovered, which is that tan is if you take sine and cosine and divide them by each other. This is a rule that's always true. So based on that, see how right here I have tan written in two different locations? I'm no longer going to write tan. I'm going to write what tan is equivalent to, which is sine over cosine. So it looks something like this. Sine over cosine minus sine over, and then see how here there's another tan? In that place I'm also going to write sine over cosine again. Make sense at all? Basically, we're doing like substitution. Is probably the best way of putting it. Well, our goal is to try to find a way to make this side of the equation look like that side, and it's not to that point yet. So I'm going to clean this up a little bit here. Make sure you close the door. Thanks. You see how the top of this fraction right here does not actually have a common denominator, doesn't go together? If I use another color, would this make sense here? I'm going to make them have the same denominator. I'm going to throw a cosine of theta on the bottom right there. But I can't just throw a cosine of theta on the bottom. I'd have to put like one there as well. Well, what this means then is now the top of the large fraction has a common denominator. So I could write it as a sine theta minus sine theta cos theta. And it's all over one large cos theta. Then the big fraction. And then really this fraction right here, I could almost write this as like a sine theta, a second sine theta, and then the cos theta. That's this one right here. I'm kind of just extending this fraction all the way over. You think you'll follow me so far?
I don't
Okay.
know what you're doing.
The y, I'm not going to be able to give you a great answer for it just yet. Can you follow the what, though? At least for the... you have a fraction on top of a fraction. We can do some canceling. So there's a cosine right here and a cosine right there. Those cancel. Which means you now have sine theta minus sine theta cos theta all over another sine theta, because that's the leftovers. Does the left-hand side look like the right-hand side yet? No, not yet. Anything else I can do with this? You'd think there's got to be some sort of canceling we can do. The problem is I can't cancel yet because the bottom is actually just one term and the top is two terms. The top, though, being a binomial, we can factor. So there's a sine and a sine in both of those terms. I'm going to factor out a sine theta. And when I do that, it leaves me with 1 minus cosine theta over sine theta, sine theta. Now I can cancel. The first sine theta that I just factored out, it'll cancel with one of the two on the bottom. It doesn't really matter which one. And now I'm left with, this is like 5 pages down, 1 minus cos theta over sine theta, which is what we had way the heck up here. Okay. That's called proving an identity. We've basically proven that this equation right here is equivalent to the other side. Yeah.
So when you're proving an identity, do you want to keep the sides separate?
You do, yeah. In order to prove something, the idea should be that if it is an identity, you should be able to just manipulate just the left-hand side or just the right-hand side. What you're not allowed to do, for example, is take this sign right here, times it across the equal sign. If it can be an identity, it should be able to be done without doing that. So like you're not allowed to, for example, take this sine, bring it up top right here, and then say, hey, look, that cancels. Our goal here is not to solve for theta, because the point is that every theta in the world, like 1, 2, 3, 7.2, all of the numbers for x or theta should all work. So that's not our goal. Our goal is to prove that side A and side B are the same as each other. Haley, you kind of asked a half question, I think, a little while ago. I don't know why we're doing this. There really isn't any sort of like practical purpose behind this, to be honest. And I mentioned before I even started here, you guys aren't going to really be asked to do this actually, because you're not going to be asked to do written response work. I still think there's some value in showing you this because these are some good algebraic skills, and if you want to keep going in calculus, the ability to kind of use your algebra skills to help solve a problem like this, those are still useful. But this is not how a question is going to get phrased. So. Okay, does that make any sort of sense? Try another one. It's one of those things where, to be honest, I'm just going to kind of example you to death today. Like, it's just a bunch of examples today. So, before I try the next example, I want to show you another one of the identities that we can use off of that list, and it's called the Pythagorean identity. You guys remember how we have like a triangle inside a circle here? If we have a unit circle, the unit circle means that the radius is 1. And that means that this side right here would be x and this side here would be y. A while back, though, we learned that cosine is equal to adjacent over hypotenuse. And the adjacent would be x, and the hypotenuse would be 1. So in a way, whatever cosine of theta is, that's going to be what the x is. And whatever the sine of theta is, that's going to be whatever y is. Well, this leads to an identity that was developed based on Pythagoras' theorem. You could say that a squared plus b squared equals c squared. That's Pythagoras' theorem. In this example here, you'd say x squared plus y squared equals 1 squared. But technically your x is a cosine squared. We put the squared, by the way, in between the cosine and the theta, just to make sure you know that you're not squaring the theta, but you're squaring the whole thing. And this would be sine squared equals 1. And this is another identity that is known to be true for whatever theta you use. It's one of the ones listed on your sheet, actually. So I'm just going to test it out real quick here. I'm going to pick the cosine of 9. And I'm going to actually choose my brackets. I'm going to go bracket cosine of 9 squared. Then I'll add the sine of 9 squared. That should equal 1. It doesn't matter what number I pick, 9, 7, 47.2, 15 pi over 3. Like, it all should equal 1, guaranteed. So that's what makes it an identity. So again, you got to change your mindset here. Our goal is not to solve. Solving is not the problem. We already know that every answer works. The key now is it's almost like a brain teaser. You're being asked to, well, not on these questions I'm showing you to start with, but you eventually will be asked to use these rules to help kind of simplify out some sort of puzzle. And it's really not a real world kind of application. It's brain teaser really is the best word that kind of comes to mind. Yeah.
So you just put a random number in there?
I just picked 9 just for but you could do it with 17 or 47.2. It should equal 1. Okay. Here are some other identities that are similar to the Pythagorean one. You can do it with sine and cosine. There are also some other ones that involve tan and secant and cotan and cosecant. So let's try another example. We're going to try to prove that this is true. I already know it's true. If I wanted to, I'd just pick a number for theta, and I would just type that same number in everywhere that we have a theta, and it should equal 2. Like, I could just plug in 9. But my goal now is to prove that it's true using some of the rules off of my list. So before I do that, I'm not really at a place where I can use any of those rules. I have to use other algebra skills. For example, what happens like if I have something in brackets squared? What does that mean? Good, you have 2 of them. So I'm going to write that out here. I'm going to do the same thing where I write out left-hand side and right-hand side. The right-hand side is just 2. I really can't actually do much with the simpler side. You know how I said one of my first rules was work with the more complicated side? It's because it's easier to uncomplicate a challenging-looking thing. Yeah. I have an analogy I was giving my grade 11s earlier this year. It was when you want to try to fix something, it's almost like the analogy of a knot. What you have to do is you have to untangle the challenging part of the knot, as opposed to like take a straight rope and put a knot into it. I don't know if that makes sense at all, but like it makes more sense to try to work with this challenging side here. So I'm going to write it next to itself. Sine theta minus cos theta next to another sine theta minus cos theta. And then next to that, I have the same thing only added. So then that's sine theta plus cos theta next to another sine theta plus cos theta. All right. Any thoughts what we could do? When you write them next to each other, what does that mean to do? FOIL them. Let's FOIL them. If I take sine and I multiply by sine, I get sine squared. Okay, so we write that like this. Sine, then the 2 theta, just to imply that the whole thing is squared, not just the angle. What happens if I do the cosine and the other cosine times by each other? Should get cos squared. And then if you do the other ones, right here, you're going to get a negative sine theta times by a cos theta. And right here, you're actually going to have another negative sine theta and a cos theta. These two things actually combine with each other. But I'm going to just keep them separate for now.
Wait, that negative one on the bottom is next to it?
Yeah, this should be next to it. I'm just running out of room here, so I'm going to put them together. Because now I'm going to do the same thing over here. These ones, when they multiply together, should give you another, let's put it over here, sine theta squared. And these ones right here should give you another cos theta all squared. And then when I put these two together, it's going to give you a sine times by a cos. And when I put those two together, it'll give you another sine times by a cos. Ultimately, there's actually like 8 different things that are here. There's 1, 2, 3, 4, 5, 6, 7, 8 different things all kind of combined here. And I've just kind of written them all staggered. They're all over the place. But like I said, think of it like a brain teaser then. Our goal then is to try to find a way to make all of this mess right here equal 2. What can cancel? Well, this sine cosine is negative. But right here, there's a sine cosine that's positive. So this one and this one cancel. And actually, the same logic applies to the one right below it. Here, there's a negative cosine and sine combo. Here's a positive cosine and sine combo. They cancel. Yeah, we've already canceled half of it out, right? One more thing. I just showed you the Pythagorean identity, which is that if you ever have sine squared and cosine squared, it's equivalent to 1. Look, right here I have sine squared and cosine squared. This little bit is equivalent to 1. And here's another sine squared and cosine squared. It's also equivalent to 1. So like Sean said, they're equivalent, so therefore you have 2. Which is what it's supposed to be equal to.
I thought that was so hard. So hard.
So think brain teaser. There's no point to this. Like I've in all of my education at the university level and teaching this, like there's not like some sort of real world problem we're solving with this. It's more of a puzzle. It's more of practicing your algebra skills than anything. Let me try another example. Let's try to prove that these are equivalent to each other. One of the ways we can just double check is I can just plug in a number for theta. I can just plug in the number 5. And both sides should equal each other. That's not our issue. Our issue is trying to prove that they're equal to each other. So we have to use whatever algebra skills and tricks you can think of to try to make it so your left hand and your right hand sides equal each other. So I guess maybe I'll just kind of I'll do it more like this. This will be the 1 plus 1 over sine theta. I feel like that's the easier side, so I'm going to kind of leave that side. And I'm going to mess around with this side right here. Anybody notice anything useful you can do right here? Unfortunately, you can't cancel them. The reason why is that this is a binomial and that's a binomial. It would be like if I gave you 1 plus 2 over 1 minus 4. 1 plus 2 I know is 3. And 1 minus 4 is minus 3. And so that means the answer has to be minus 1. But if I cancel these ones right here, 2 over minus 4 is not minus 1. So although that doesn't work, there is a canceling you can do. You can factor the bottom. Yeah, that's a good place to start. What you can do is you can actually factor both. The bottom has a sign in both parts of it. So you could say that you have a sine theta. You can take that out, and what it leaves you with is a sine theta minus 1. And I'm just going to pretend that sine theta is like x, in a way. The top is a difference of squares. Good. X plus 1, x minus 1, except x in this case is sine theta plus 1 and sine theta minus 1. Now you can cancel the right section, obviously, right? You can cancel this binomial with each other. And what you're left with then is sine theta plus 1 over sine theta. At this point, it might be a good example to show that you don't have to exclusively work with one side. What you could do is start working with the other side now, and you kind of meet in the middle. For example, right here we have one combined fraction, and right here we have two separate fractions. So one of the things you've learned at some point, because I know I've taught you this, is that you can combine fractions using common denominators. This 1 right here is like 1 over 1. I can make it like sine over sine so that it has a common denominator. Basically, I'm just taking the 1 and the 1, and I'm just making it into a sine over a sine. Because now that they have a common denominator, that common denominator is sine theta, and the top part is sine theta plus 1. And look, now each side is equal to each other. So yeah, they are equal. Something like that. Wait, if this is something that you feel like you're good at, or this is something you can handle, I found for me this is a good indicator of whether or not your algebra skills are probably strong enough for continuing on if you want to like do university level calculus. I should remind you though, you're not going to be asked to do this. I'm going to ask you to do this like 3 or 4 times, and that's about it. Okay. I'm going to have other tricks for how to solve diploma level questions, but these are some of the skills that are kind of involved. Why don't I skip ahead and try this one here? This one's maybe a bit more challenging. I think I have some diploma questions hidden in this booklet too somewhere. I do too. Okay, why don't I try this one here? This one looks fairly challenging. And then maybe I'll try the one after it. We'll do those two. And then after that, we won't do this whole left-hand thing, right-hand thing anymore. Then I'll walk you through some diploma questions because that's what you're really going to get assessed on instead. But let's do this twice more just to kind of practice. Right here, you've got some fractions. You have some skills of working with fractions. And over here you have a cotan. So I might suggest that probably the easier side to work with, even though it is uglier, is I think we should probably focus on this side right here. When we have two fractions, can the fractions actually go together? All right, to do that, they need common denominators. And boy, these guys look like they have common denominators, but they don't. So let's give them common denominators. I'm going to need a cosine of theta over that secant of theta minus 1. And to make this work, I'm going to have to times by the same thing top and bottom. It'll be secant of theta plus 1. Secant of theta plus 1. I'm just going to bracket this thing to death. Basically, I'm taking this thing right here, and I'm putting it on the top and bottom. And then I use the reverse logic for the other section here. Here we have the cosine of theta and the original secant of theta plus 1. And I need to put next to it the secant of theta minus 1. First step, I common denominated this thing. Alright, well, once I have common denominators, I can just throw everything on big 1 denominator. So it's going to be secant of theta minus 1 and secant of theta plus 1. The top, I'm going to FOIL a whole bunch of stuff. I'm going to do cosine times secant. That's this one times this one. I'm going to do cosine times 1, so that'll just give you cosine. And then here I'm going to do the exact same thing. Cosine times secant. And I'll do cosine minus 1, so it'll be a negative cosine. Well, there's a couple of nifty tricks I'm going to play here. I like to think of them as tricks. Something cancels. Good. Because you have one positive cosine, that's the second thing written. You have a negative cosine, that's the fourth one written. So this guy right here, and this guy right here, they cancel. Does that make sense? You are left with 2 cosine secants. Because there's one of them right here and one of them right here, so now there's 2 of them total. On the other hand, down on the bottom, technically the bottom of this thing could probably also FOIL out. I'm going to try to save some room by just doing it in my head. This one times this one will give me a secant squared. And this one times this one will give me a negative 1. They would, yeah. Because what you'd get here is a negative secant and a positive secant. So I'm just going to skip that step. I think now is probably a good time to play a few more of the tricks off of our formula sheet. One of them involves secant. There is an identity about secant that I can use right about now to help. What is secant equivalent to? Can you find it? Yeah, secant is equivalent to 1 over cosine. It's what's called the reciprocal identity. So what I could do right here is rather than writing secant, I could write 1 over cos. The reason why that's useful is what happens when you take a cosine and you times by a 1 over cosine? Yeah, it just gets rid of it. Yeah. On the bottom of this fraction, I have secant squared minus 1. And there's one very similar to that on the formula sheet. I'm just going to find an example here. There's this one right here. Now, it's not exactly as written. You see how right here there's a secant squared? But then there's a plus 1 on this side right here. If I were to take this minus 1, or this plus 1 off of this side, and put it on that side over there, you see how I'd have a secant squared minus 1? Well, secant squared minus 1 is equivalent to tan. So going back to our problem, rather than writing this secant squared minus 1, I'm going to write tan instead. I think it was tan squared though. All right, well, what does that mean I'm left with? It means I'm left with 2 times 1, that's kind of pointless, over tan squared. That's about as far as I'm going to go on this side here. I'm going to go back over to this side for a second here. Yeah, because that's literally the definition of cotan. Cotan, there's a rule about it that says 1 over tan. So I'm going to leave the 2 on top, and I'm going to put the tan on the bottom instead, because that's what cotan means. Cotan means take tan and throw it on the bottom of the fraction instead. And now I've proved that these 2 things are equivalent. Absolutely. No, you don't memorize those. Let me do one more, and then I'll show you some actual diploma questions. Because, like I said, you're not going to be asked to do this. I'll ask you to do it a few times because I think it's worth practicing, but this is not what you're ultimately going to do in this course. How am I doing so far, by the way? Is this something you can follow at least? Doing it yourself is challenging. Like, being able to do this without help requires a lot of patience and perseverance. I kind of, well, I've done this a lot longer, right? So I kind of know which tricks to play. Okay. Yeah, you have to like press the power button or something like that because it falls into sleep. Yeah. On this particular one right here, if I break this up into my left and right hand sides again.
Where is that one?
The next one. There is a trick you can play if you're really, really stuck. Like at this point right here, as I look at this question, there's actually not really a lot I can do. It's quite frustrating. So one of the tricks you can play is you can multiply by what's called a conjugate. We did this last year in grade 11. It's been a while. See how the bottom of the fraction right here is 1 minus cosine theta? The conjugate of 1 minus cosine theta is 1 plus cosine theta. And so I'm going to multiply this side by 1 plus cosine theta over 1 plus cosine theta. Just gonna bracket all this stuff to death. What should end up happening now is the top of my fraction is going to be sine theta next to that 1 plus cosine theta. But the bottom of this thing right here, I'm going to FOIL it. It's a difference of squares. So when you do 1 times 1, you'll get 1. And when you do the cosine in the 1 and the 1 in the cosine, those will cancel. When you do the outside two terms of negative cosine and positive cosine, you'll get a negative cosine squared. Okay, I've worked with this enough to recognize this. I'm hoping that the more we practice this, the more you guys will get good at recognizing that this is kind of something similar to your formula sheet. There was a rule we learned, I even proved it for you, that said that sine squared plus cosine squared equals 1. This is not quite the exact same, the thing that I've dotted, but it's kind of similar. In order to make it the same, I'd have to bring that cosine to the other side and make it 1 minus cosine squared. So what is all of this stuff equal to then? Exactly, sine squared. So then I can write it again as a sine of theta. I'm not even going to FOIL this, I'm just going to leave it there. Plus 1 plus the cosine of theta. And this is all over the sine squared theta. What did you say?
Like there's like two sides that go together, so like could you cancel one of them or like?
Sure. So why don't I write it like this? The two sines, there's like 2 of them.
And then could you cancel one of the sides?
Yep.
And then they're equal.
And then you're equal to the other side. Yeah.
I get it now.
Cool.
Oh, there's no square there?
Well, there was a squared there. This was supposed to be sine squared, but I just wrote it twice. I wrote it next to itself, just so that maybe you can visualize that it can cancel. This is what I was taught, and this is what, to be honest, I taught all the way up until they changed curriculum. And when they did a curriculum change, they got rid of written response. And in terms of getting rid of written response, it means that you don't have to do this anymore. But the skills that I've been showing you here, you still need to have those skills, but you have to use them in a different sort of problem-solving context. So why don't you guys take a break, and then when you come back, let's do some of the diploma questions that are next. Because I've actually shown you what I need to show you. It's now I need to let's show you what you're going to get assessed on instead. So go take a 5-minute break. Okay, why don't we try some diploma questions now? I find this section one of the most frustrating ones for me to teach because in terms of the outcome that I'm supposed to teach you, I'm supposed to show you how trigonometric identities work. I feel like I've covered that. There's a bunch of formulas, use the formulas. But like that's not enough, right? So what I want to do for the rest of whatever we do today, I don't think we'll start the next section. I think this is enough for today. Let's show you some diploma questions so you get a sense of like how are you going to be assessed on this? Because it's not going to be what I just did with you guys. It's going to look different. So here's some variety. Here's the first one. I put this one first because this one's probably the easiest one. One of the ways that you can prove an identity is to do all that work we just did. Or another way you can do it is just plug in a number for example, you could plug in 2.1 right here and see what this side equals. You could plug in 2.1 right here and here and here and see what the other side equals. And if they equal the same thing, which they should, then you've proven that this thing is true. So really what this question then says is if you substitute 2.1 radians, what does each side equal? So let's try that. Can you type in a cotan though? Okay, so you do have to have some knowledge of identities and recognize that a cotan is when you inverse a tan. And you have to square it. So it'll look something like this. Bracket tan of 2.1. I'm going to square it, and I'm going to inverse it. I hope my calculator will do this right. Some of your calculators might actually throw another bracket on before you throw the -1 up there. I hope mine does this the same. Well, let's just double check. Make sure we're all in radians before I go any further. Do you get that number? Okay. I still haven't added the cosecant part though. So I then have to add the cosecant. But again, I can't actually type in a cosecant. What I can do is type in a sine of 2.1 and square it. No, not square it, inverse it.
I didn't get the root that number.
Are you in degrees or radians? Let's just double check that part too.
I'm in radians.
Okay. Here's what I'm hoping you guys get for that step. Because you've got to square it, and we've got to inverse it. Alright. So this should hopefully be our answer. Let's just confirm we should try the other side of the equation, also typing in 2.1, and seeing whether we get 1.50. To try the other side, it's a bit more complicated to type in. I'm going to use a bracket for the top. Then I'm going to use another bracket, and I'm going to cosine 2.1. I'm going to square it. Then I'm going to add the sine of 2.1. You need to count your brackets to make sure you have them all right. Here is a bracket around that 2.1. Then this one and this one is a bracket around the cosine so you could square it. These ones are the ones around the sine of that 2.1. I still have one bracket right here, which I've left so that I can have the whole top of the fraction in a bracket. And then dividing, I'm opening up a new bracket for the sine of 2.1, but that needed to be squared. And if all goes well, this should also equal that number. So there you go. Does that make sense? I think that's a pretty easy question altogether. Like, that's not the most challenging one, but there's an example of how you might get assessed on this.
On the first part, what did you do to get 1.5 after 0.5?
Oh, I still had to add 1 over sine of 2.1, because that's what this little bit right here is. The cosecant is a 1 over a sine of 2.1. So I had to add that number too. Okay, you know how when we first started the lesson, I showed you what I was taught, which was like to do a left-hand side and a right-hand side. And you try to make the two things equal to each other. This is probably the most common way that they'll phrase a question along these lines. They'll tell you what one of the sides, let's spell it right, Chris. Cotan. They'll tell you what one of the sides is equivalent to. And what they're going to not do is they're not going to tell you what the other side is. And then they're going to ask you to like manipulate this as far as you can get until all of a sudden you get one of these 4 answers. Does that make sense? Like they can't do it quite the same way I did, but they'll give you a complicated side, and then one of these 4 answers is the other side. So really we just need to focus on this thing right here. Well, there's actually not really a lot I can do. None of these things really scream something fancy, except for one. And I just have enough experience, I think, to... Like, experience helps. The more you do this, the better you get at it. I recognize that cotan squared is something on your formula sheet. It's not perfect, I think, but if we rearrange, we can find something that involves a cotan. See how this one right here has cotan squared plus 1 equals cosecant squared? How can I get cotan then by itself? Okay, so what I could say then is cotan squared is equal to the cosecant squared if I minus 1. That's what I'm going to try. I'm going to try to take cosecant squared and I'm going to minus 1. So this guy right here, I'm going to write this as a cosecant squared minus 1. If I do that, I'm just going to kind of combine this all into one step. What you'll have then is a cosecant squared. You'll have a regular cosecant, because that's this one right here. I guess I should go with x rather than theta. You see how there's a minus 1 and a minus 4? That makes minus 5. And that's A. It probably won't be nearly as many steps as the ones I showed you to start with. Like it might be 1 or 2 steps. But it'll be your goal to figure out how to manipulate one to the other. That makes sense? I'm just going to change this to an X right here. That was a little ugly. Okay.
Kyle Blood, can you please call 100? Kyle, please call 100.
So here's a question where I'm telling you what sine is equal to and what tan is equal to, and our goal is to figure out what cosine is equal to. And one of the ways we can do this is using the identity that involves sines and cosines and tan. Because there is one that involves those. I don't know that I talked about it a bunch, but there's one that says that tan is equal to sine over cosine. Does that make sense? Well, how could I rearrange this identity to get cosine by itself then? Sure, so basically those two things are flipping places. Okay, so if I write it like this, does that make sense to everybody else? Ooh, there's muffins today. Thanks, guys. I guess it's just you today. Thank you. Is everybody okay with this step right here using that identity there? Yeah. Because now we know what sine is equal to. Right up here it tells you that sine is equal to m over n. And tan is equal to m squared over n cubed. I close that door, those junior houses. Does this make sense so far? Alright, well now cancel. This m and this m right here, well actually maybe it's better to write it like this. Have I ever shown you guys that dividing fractions you can multiply by reciprocals? You guys know this trick where you can write m over n, but then rather than dividing you can multiply if you flip this one upside down and do this. I've shown you that trick at some point, right? Because now what can happen is this m and that one can cancel, and this one and that one can cancel. And what we're left with is n squared over m. That makes sense? Try another one. Okay, so this one's kind of similar to one we just did 2 questions ago, where they're giving you one of the sides of the equation, and we're just going to mess with this side right here until we get one of the 4 answers. Students sometimes find this very frustrating though, because you don't know which one is the right one, so you can kind of look at these 4 and try to aim to try to make it one of them. No, but really, you just have to keep like playing until you eventually get one of these 4 questions. Again, maybe the best way of thinking of this is it's more like a brain teaser. Like think of it as a puzzle as opposed to some sort of purposeful math question, because I cannot think of a place where this is useful, like as this. So, 1 plus tan squared though. I'm hoping that after a while, the more you do this, the more you recognize, hey, that's on our sheet. Maybe it's not exactly like that on our sheet, but there's got to be something involving 1s and tan squared somewhere.
It's exactly that.
Oh, it's exactly that. Perfect. Okay. Okay, this one right here is not perfect, I don't believe, because it's the Pythagorean theorem one, which is like 1 is the same thing as the sine squared and the cosine squared. But if I bring the sine squared to the other side, this stuff right here would be equal to cosine squared. Does that make sense? So what I could write this thing now as is it's secant squared over cosine squared. All right, one of these involves a square root remaining, but 3 of our options the square root leaves. I think I can see why the square root leaves. We now have numbers that are square rootable, because both the top and bottom of the fraction are square rootable. So this should be equivalent to just secant over cosine. Because I should be able to square root them all, right? Okay, just need a little more context. What is a secant? Yeah, a secant is a 1 over cosine. But then you're dividing by another cosine. Well, this is really like cosine over 1 then. So you gotta be careful here. This cosine is on the bottom of the top fraction, but this cosine is on the top of the bottom fraction. They don't cancel. They actually combine. If you want to use that same rule I just reminded you of, you can take the second fraction and multiply it if you flip it upside down. Like you're going to flip this guy upside down. It's called multiplying by a reciprocal. What ends up happening is you have 1 over cosine, but you have like 2 of them. Well, that's not any of these answers, but yeah, it kind of is though, because isn't 1 over cosine also known as secant? So then it's secant, but it's secant squared, because there's 2 of them. You can see how this is kind of similar to what I showed you before, but it's not quite the same. One of the nice things though is you know what the 4 possibilities are, so you can try to aim for some of them at a certain point and be like, okay, I'm going to try to make it equal to this one. For this one right here, I'm going to use my identities wherever I can try to find them if they work. Like for example, here's a cotan. Anybody know what a cotan is equivalent to? Not a cotan squared, but just regular cotan. 1 over 10? Right, it's 1 over 10, but there's another one for cotan we can use. Cool. It's also cosine over sine. Why is that useful? Yeah, you can cancel the sine signs. Sine signs. Hey, it's a little more power. All right, what's a cosecant equal to?
1 over sine.
Yeah, 1 over sine. And then tan is equal to sine over cosine. And the reason why that's useful is, again, the sine signs cancel. All right, what am I left with then? On the top of the fraction, I'm left with m cosine x. If it's okay, I'm going to write it as over 1. And then on the bottom of the fraction, I've got 4 times 1, so I'll just call it 4. And on the bottom of the bottom, there's an extra cosine. We've had this issue before. It's actually been the last 2 questions in a row. You have multiple fractions being divided by each other. Take the bottom one, flip it. So let's write it as m cosine x over 1, and we'll multiply by cosine x over 4. Make it equal to 8. So I'm just taking the second one here and I'm flipping her upside down. I've done about as much as I can, I think, at this point here. Now I'm going to actually read the question. It says, what is the value of m? Okay, so now I actually can bring things across an equal sign. This is not about an identity anymore. This is more about, can we solve? So how do I get this m by itself? Well, there's this 4 down here. How do you get rid of a 4? Times it up, which means that 8 times 4 is 32, which kind of starting to look pretty good here. Actually, there's a 32 even there. There's a 1 right here, but that I don't think we really need to do anything with that. How do you get rid of this cosine and that cosine? Yeah, divide them. So it means you need to put the cosines on the bottom, and there's 2 of them. So I'll write it like that. And we actually just came across this issue, the last question. Cosine on the bottom is the same thing as secant. So you have 32 secants. That is what m equals. It's like a brain teaser. You know what I mean? Like there's no point to this, other than someone's going to give you a test on it. But I mean, it is useful still. Like it involves logic skills. I think those are still valuable. But I cannot give you a real world application for why you'd use this. What do you guys think? Is this coming along okay? Do you want to try a few on your own, or are we still at the place where I should walk you through some? Sean's shaking his head no. Everybody else, what do you want to do? How confident do you feel? You want to try it? All right, try the next one by yourself. See whether you can try to answer this one without me doing it first. I mean, we've done stuff kind of like it before, right? You have to use your algebra skills, and there's no one way of doing it. That's one of the frustrating things. So you're just going to kind of play around until you can try to make this top thing equal one of those bottom 4. One thing I haven't mentioned yet, sometimes there's more than one way of solving a question like this. Like there's not always just, you know, this is the way of solving it. Sometimes there's more than one way to get the right answer. Let me give this a try. Let's see whether you guys get solved the same way I did. There's more than one way of solving, but this sine over tan, we've been working with fractions a lot recently. You can almost write it like sine over cosine. And what ends up happening then is these signs can cancel. I just want to make sure I do it properly. It's almost like it's sine over 1 over sine over cosine. So I'm going to write it as sine over 1, and I'm going to flip it to make it cosine over sine. And the sines do cancel, but what you're left with out of this mess is cosine. This one right here, let's see if this logic makes sense. If secant is the flipping of cosine, then shouldn't the flipping of secant become cosine? No. So that means that this guy right here is a second cosine. And so therefore you have two of them.
See, how I thought of it is because secant is 1 over cos. I thought you could do 1 over cos on the right side.
And then you like flip that bit?
Yeah.
That's the same logic. Yeah, you don't, yeah, different way of doing it, but you have the same answer.
Yeah.
Wait, can you repeat what you just did?
So what Sean did here is he said that secant is 1 over cosine. So he did 1 over cosine. And then we've had this fraction issue come up a lot recently where you have a fraction over another fraction. So he just flipped the second fraction, which gives him 1. And then it's cosine over 1. And I guess you can cancel those if you want. It doesn't really matter because it is a cosine when you're done. Try another one. Let me give you a little context to this one, by the way. This question here, what ends up happening is when you take all 4 of these things here and you simplify them, they should simplify to a single number. Like, for example, I'll do the first one with you. If I give you 1 over 9 secant cosine, what is secant equal to? Okay, so it's 1 over cos, but then you have a cosine. What will happen is the cosines will cancel, and the only thing left is 1 over 9. All of these things here should simplify to purely just a number. We're then going to rank them from lowest to highest based on how big their numbers are. So, like I said, it's kind of a puzzle in a way. Is cotan equal to 1 plus cosecant? I don't have a sheet in front of me. Cotan. What is cotan equivalent to? Is there one for it directly on your sheet? Oh no, cotan squared, sorry.
Oh, there's the cosecant squared. Minus. Yeah, minus.
Okay, so cotan squared is equal to cosecant minus 1?
Cosecant squared.
Cosecant squared minus 1. So then if you plug this little bit in for that one right here, that means that you should cancel the cosecant. So this one should be minus 1 then. Is that what you guys got? Did you solve that one? This third one right here, I don't know if this logic makes sense, but if sine squared plus cosine squared equals 1, then shouldn't 2 sine squared, 2 cosine squared, shouldn't that equal 2? If you had to prove it another way, you could factor out the 2. You could say you have 2 sine squareds and cosine squareds. But then if all of this is equal to 1, then this thing right here, hopefully you'd say it equals 2. Does that logic make sense for the third one? For this one here, cotan is really equal to a cosine. Cosine over sine? Over sine. Which means what you have is 2 times 2. And then you have cosine squared over sine squared. Is that not working here?
But doesn't it also work the other way because the cosine squared or the cosine over sine is equal to cotan?
Yeah. I was thinking this should cancel, but it's not canceling, is it? Stuck on this one too. I feel like that's got to be a typo. I thought this one was going to just straight up cancel. Because cotan is cosine over sine.
So could you change that side to cotan as well?
Yeah, it just means you have double the you just have 2 cotans then. But that doesn't actually give you a number. I feel like this one should have been a typo. Maybe this should have just been tan. Because if it was a tan, then it should have been like, say, a sine over a cosine. And then you'd cancel that one and you'd cancel this one. Let's assume it was a typo for right now, and I'll have to go look it up later. I don't remember this one anymore. And if everything cancels, then you'll have 2 times 2, so it'll equal 4. I think that's supposed to be multiplication. So then, anyway, long story short, ranking them from lowest to highest, I guess this one's the lowest because it's negative. Then the 1/9 is next. Then the 2 is next, and then the 4 is last. That's how you solve that one. Let's assume that was a tan, not a cotan. I don't know how you solve it otherwise. Because it has to equal literally just a number. Did that make sense otherwise? Yeah. Okay, you know what? I mean, why don't I just leave the last ones for you guys to try on your own? Because I think I've done enough for the day. Let me just give a quick summary then. When it comes to identities, this is not very purposeful. I don't know that it's necessarily hard. I mean, it can be challenging. It is tricky, but it's more of a puzzle than anything. Your goal is to use these rules that are on your sheet and use them to, I don't know, help solve a problem, I guess. Some sort of puzzle. We've gone through about half of them. We'll do the other half tomorrow, I think is probably the best way to use our time then. So we're not doing them all at once. But really, it's more of the same. Once you get the hang of how to use these rules, then that's what you do. The point, though, is not to solve for theta. So don't try to isolate and get theta by itself, because it's not going to happen. Like, it's not even possible. One of the reasons why is that every single answer for theta in the universe works. 1, 5, 7, 2.3. So, does that make sense? I would say that probably one of the best ways to get better at this section here is just the more practice you do, the better you get. So, yeah, why don't I stop here, and you guys can try those last questions on your own, and then tomorrow we'll do the second half of the notes. Does that work? All right.